We understand how to compute the standard error associated with a set of measurements, which represents approximately a confidence interval of 68.2%. We need to discuss how we can use the student's t-distributions to estimate confidence intervals at different levels of certainty. The objectives for this lecture are to gain an understanding of the student's t-distribution, or actually the student's t-distributions, and use the student's t-distributions to specify confidence intervals for a set of measurements. We already know that when we take samples from a population and use those samples to estimate the mean and standard deviation of the population, some uncertainty is going to exist in those population estimates. You can probably imagine that the certainty of the estimation of the population mean and the population standard deviation will increase if we take a larger number of measurements. The student's t-distributions, which interestingly were derived as a result of batch processing in brewing Guinness beer, are a set of probability density functions that are much like the Gaussian distribution. A set of students' t-distributions are shown in this graph right here. And we see that there are a number of different curves. That's why they are a set of probability density functions. Each probability density function has a different shape depending upon this parameter, which is called the number of degrees of freedom. The number of degrees of freedom are based upon the number of samples that were used to estimate the population mean and the population standard deviation. This relationship is that nu, which is the symbol for the number of degrees of freedom in the system, is equal to the number of samples that are used to estimate the population mean and standard deviation minus 1. If we take an infinite number of samples of our population, what happens is that the student's t-distribution for a large number of degrees of freedom is going to be identical to the Gaussian distribution, which is the black line shown here. If we have fewer samples, the student's t-distribution still looks a lot like a Gaussian distribution. If we have fewer than an infinite number of samples, we see that the probability distribution function for the student's t-distributions with less than a large number of degrees of freedom is going to look a lot like the Gaussian distribution. However, it is going to have a broader width to it, and the tails here are going to include more area on the outside of the tails. This is important because we'll recall that integrating between limits of under the probability density function provides the probability of observing a value within those limits. Of course, we can also ask or state the problem in a different way. We can determine the number of standard deviations that are necessary to obtain a desired probability level or confidence interval. These limits of integration that are required to obtain a desired probability or confidence interval level are known as the critical t-value. So to assign a confidence interval at a known probability level, we need to know three things. We need to know the number of degrees of freedom, which again is defined as the number of samples that are used to estimate the population mean and standard deviation minus 1. We need to know the desired probability for the confidence interval, and that should say for the confidence interval, which is going to be denoted by the letter P. And finally, we need to discuss how to use the inverse t-distribution tables or inverse t-distribution calculators. T-distribution tables and calculators are based upon the type of integration that is being performed under the different t-distributions. So there are two types. One is called a single-sided or a single-tailed distribution, and the other one is called a double-sided or double-tailed distribution. A single-sided distribution is when we integrate from negative infinity up to the positive critical t-value that is going to give us the desired probability level. Now remember again that when we integrate under the distribution, we obtain the probability that we're going to obtain a sample from the population within those limits of integration. If we integrate from negative infinity to positive infinity, we should get a probability of 1, or 100%. The remaining area under the curve that is not included in the integration, we're going to call our alpha level. Now the double-sided or double-tailed integration is going to integrate the probability density function between two critical limits, or two critical t-values, one being a negative critical t-value and one being the same positive critical t-value. Of course, this double-sided integration is going to include areas on both sides of the distribution that are not included in the integration. For the double-sided integration, even though the alpha level is the same for that of the single-sided integration, the probability under this curve or the area integrated under this curve is going to be less because we have these two tails that are going to account for this same alpha level. Critical t-value tables and calculators are based upon the probability that the value that we desire will not be contained within the range of integration. So therefore, all of the tables and calculators are going to be specifying this alpha level, not the desired probability level. To calculate that alpha level, for a single-sided integration, we're going to take that 100% probability and subtract from it the desired confidence interval probability level and divide by 2. For a single-sided integration, we only need to take that 100% probability and subtract from it the desired probability that we wish to calculate the confidence interval to find the alpha value. So it's very important when you're using these tables and calculators to understand whether it's using a single-sided integration or a double-sided or double-tailed integration. Now that we understand this, we can use the student's t-distribution tables. The first thing that we need to recognize is that most tables are going to tell us whether it is a single-sided or double-sided integration. And in this example right here, we have a single-sided integration because we're only looking at the area, the shaded area under the t-critical value that is on the right-hand side of the distribution, indicating that the integration is going to occur from negative infinity all the way up to the critical t-value. The t-table has a number of rows and columns. The columns correspond to the alpha value, or the shaded area, that is going to correspond to what is not included in the integration up to the critical t-value. And the rows are going to correspond to the number of degrees of freedom. Knowing that we're working with a single-sided distribution, we can rearrange the equation that was on the previous slide to determine that the probability level for our confidence interval is going to be equal to 1 minus 2 times the alpha value. So we can now go along and determine what the probability level is associated with each of these alpha values in the table. So this one would be 80%. Right. This one would be 90% here. 0.025 would correspond to 95%, and so on and so forth. Recall that the number of degrees of freedom are related to the number of samples that are used to estimate the population mean and standard deviation. So now that we know what alpha value we need to use and which row we need to look in to find the number of degrees of freedom, if we want to, say, determine the confidence interval for a 95% probability with 6 degrees of freedom, we would just correspond the row and the column and find that the critical t-value is this value that's given in the table right here. You can use Excel as a calculator to determine the critical t-value by using the t-inverse function, because basically what we're doing is we're taking the t-distribution value and we're taking the inverse of the integration to determine the critical t-value. The T-inverse function requires an input of our desired alpha level as well as the number of degrees of freedom. And it's important to understand that Excel uses a double-sided integration or two-tailed integration instead of the single-sided integration that was used in the table example that I showed previously. With all of that information in hand, we can now return to our load cell measurements example. And if you'll recall from the previous lectures that we had 10 load cell measurements when we applied 10 pounds of force to that load cell. And based on the measurements, we came up with these parameters. So we know that the number of samples is 10. We came up with a mean of 0.411 volts of output for the applied 10 pounds of force. And we came up with an estimated standard deviation of 0.01 volts based upon those 10 measurements. Recall that this standard deviation here represents a confidence interval of about 68%. If we want to compute the 90% confidence interval associated with these measurements here, we first need to determine the number of degrees of freedom, which is the number of samples minus 1. So in this case, for this example, the number of degrees of freedom is going to be 9. The other thing that we need to know is the alpha probability level associated with our 90% confidence interval level. And that's going to depend upon the method that we use to calculate the critical t-value. In this example, I'm going to use the t-distributions table. And in this t-distributions table, we recognize that this is a single-sided distribution. So for a 90% probability level, our alpha value is going to be given by this formula right here. And we know it's going to be 0.05. Now that we have the desired alpha value and we know the number of degrees of freedom in the system, to calculate the critical t-value, we're just going to find the 9 degrees of freedom and our desired probability level, here our desired alpha value, and go across and down to find that the critical t-value is 1.833. Of course, if we did this in Excel, we would have to recognize that Excel uses a two-tailed distribution, so the alpha value that we would input into the function would be 0.1 instead of 0.05 as it was for the table. Entering this into Excel gives us the same result that we got using the t-distribution table. Now that we have the critical t-value, the way that we get the value of the confidence intervals with that at that 90% confidence level is to simply take the t-value that was associated with the desired confidence interval level and the number of degrees of freedom, and multiply that by the standard deviation that was estimated from the population. Running those numbers with the example data that was provided is going to show us that when loaded with a 10-pound force, the load cell is going to provide an output of 0.411 volts plus or minus 0.018 volts with 90% confidence now. Now it's your turn to pause the video and see if you can use the techniques that were described here to calculate the 95% confidence interval for a single measurement and the 99% confidence interval for the single measurement. Once you've done that, you can compare your result to the results shown here and see if this is what you were able to determine based on the method that you used. Now so far we have looked only at the uncertainty associated with a single repeated measurement. That is, what are the bounds or the expected bounds if we take one additional sample from that population. Now we can improve or reduce the uncertainty if we were to take multiple repeated measurements from that population. If we take multiple repeated measurements from that population and then we average them together or take the mean of those multiple repeated measurements, it's more likely that we are going to be closer to the actual population mean. So this means that the confidence interval is going to be a smaller limit about that mean value. So if we take k repeated measurements from that sample population and then we take the average of those k measurements, we can determine the confidence interval for this mean of multiple measurements by the standard method that we just used, except for now we're going to divide the standard deviation and the t-value by the square root of the number of samples that were used and taken and averaged together. The best way to describe this concept is with an example. So we're going to return to the load cell example, and now what I'm going to do is take 5 measurements of that load cell output when I apply 10-pound load to it each time. So based on the data that we acquired with the load cell, we know that it has a estimated mean of 0.411 volts when we apply 10 pounds of force to it with a standard deviation of 1/100th of a volt. Therefore, at 90% confidence, if we were taking a single measurement, we would expect a single measurement to fall within 0.018 volts of this mean. However, if we take 5 new measurements, and by the way, this should say K, where K is equal to 5, if we take 5 new measurements with 10 pounds force applied to the load cell and we average them together, we expect the mean or the average of those 5 new measurements now to fall within a smaller band around the mean of 0.411 volts. So in this case, that's going to be 0.0082 volts. And with that, we have concluded the discussion of confidence intervals and how to compute confidence intervals based on a set of repeated measurements. Next, we're going to look at how to properly perform a linear calibration and account for the uncertainty in that linear calibration.